Okay. All right. Hello again. One more hour. So I was telling one of your colleagues that I realized the videos should show now the writing in the correct way, orientation, because I watched the video, a piece of the video again, and it seems okay. The only problem is that I need to remember to unshare, stop sharing the screen. Otherwise, what I write is just a small window at the bottom. I'm sorry about that. I'll make sure that that's something I remember to do. So before we continue, I completely forgot to show you the syllabus, which I'm sure you all looked at. It's very, basic, but you have my email, and you can write messages on Teams. But also, this is my US cell phone, and if you have WhatsApp, for example, it's an easy way to reach me. Or if you have an iPhone, I guess you can send me an iMessage. So the main thing that I wanted to briefly point out is that in the list of topics, of course, I have topic and number of hours, but I cannot guarantee that I will dedicate the exact amount of hours that I'm listing here. That was just a guess. But I do have quite a bit of hours for the two homeworks. And by the way, I just checked with the professors organizing the PhD in Naples, and it is okay for me to assign you the final the homework 1 and 2, and you can finish them up after the 31st. I think it's more productive if we try to work on them together until the class is on, and that's the reason why I have all these hours dedicated to that. So maybe this week, later on, and definitely next week, there will be a couple of sessions where we I won't instruct, but I will be available while you work on Simulink. Does that sound like a good plan? Otherwise, we can cover more topics, of course. All right, silent consent. So let's finish this up. Maybe it won't take an entire hour, actually. But we were talking about quaternions and the DCM in terms of quaternions, and we're here at the differential equations. So this is the equivalent of what we have seen with other angles. Is these three equations are the ones that give you the angular velocity as a function of the quaternions and their first time derivatives, like you've seen with other angles. You had an expression that had omega equal a matrix containing sines and cosines of the quaternions. I'm sorry, of the other angles, and then the time derivatives were vectors separated. So of course you can put this in a matrix form, but it's pretty much the same idea. You have the angular velocity vector, which is equal to, you could put this in form of a matrix that contains quaternions, and it multiplies the time derivatives q1 dot, 2 dot, 3 dot, 3, 4 dot of the quaternion itself. The way to get to this expression is basically you take the DCM, and take the time derivative and differentiate the norm condition. The norm condition means this one here, that the q1 plus square plus the other element square has to be 1. So it's a tedious algebraic exercise that you can perform, but that's what you get. And this is the norm condition. So if you solve for the q dots from these three equations, so you invert basically this system of three equations, and actually system of 4, because you have this fourth one here, you can also find the one relationship that we would use, as you can imagine, if we want to numerically integrate now the quaternions over time instead of the other angles. And so now you have the expression of the q dot, which is 1/2, it's a constant, quaternion matrix that are called capital Q, and now we have a 4-component vector, just the last one is a 0. So it's basically the omega vector. Now the beauty of this is you will find no issues when you integrate numerically quaternions. There's no singularities, there's no sines, cosines, there's no divide by something that could go to 0. No trigonometric functions. They're also more computationally efficient, especially on small microcontrollers. So there's a lot of advantages, with the obvious disadvantage that if you give me a quaternion, I have no way to visualize what it means in terms of orientation. If you give me three other angles, I can kind of play with my reference systems and coordinate systems and draw something that is kind of meaningful, even though it's still very difficult, but we're talking about angles. While with quaternions, is really not that intuitive. But again, you can always go to the DCM. You have the quaternion at any given time. You go back here, put together the DCM, and extract from the DCM the other angles, which is something that we have not done. But if I go back to those images that I showed you, here it is. These are basically the DCMs put together with the 12 possible combination of all the angles. And so, for example, if you have, let's see, the 3, 2, 1 expression here, and say that you have the DCM, which is 9 numbers, what you would do to extract the corresponding 3, 2, 1 other angles is, well, for example, go to this last element, the element 1, 3, and perform an arcsine function, change the sign that gives you theta. Once you have theta, you can go here and extract phi, and so on and so forth. And then you can, of course, extract psi. So by using arc cosines, arc tangents, arc sine functions, you can, from the DCM, of course, extract the other angles. And so if that's what you want, you can always do so. Always keep in mind that no matter what you're using, other angles, quaternions, there's many other representations, to transform from one to the other, you go through the DCM. Other properties when we use quaternions that are important, if you have successive rotations, of course you can put together the DCM, and so if you have a rotation from A to B and then from B to C, you multiply the matrices, and that's the obvious. It's exactly what we had done when we seen other angles, and we have multiplied those simple rotation matrices to get the final DCM with the 3, 2, 1 sequence. You can do that, but there's also another way, which is the one reported here. So if you have two quaternions, Q prime and Q second, and your rigid body goes through the first rotation and then the second one, you can multiply them according to this matrix vector product, and that gives you the actual quaternion. So go from A to B and then B, C. If you want to go from A to C, you multiply the two quaternions for the two successive rotations according to the expression like this. Again, no sines, no cosines, just matrix products of the quaternions themselves. If you change signs to all the elements of a quaternion, you get the same rotation. You can easily show that by its definition. If you change theta to theta minus 2 pi, you get the same orientation, but you have rotated in different ways, one way or the other. And the quaternion that has the positive last element between the two options will give you the shortest rotation. That's something, again, go back to the definition of quaternion. Remember what we have done. This is the initial definition. It's just properties of sines and cosines functions, really nothing special. One note, since we're here, in many books and many people may show you a different quaternion where the scalar component is cosine is actually the first element, and the vector part, E1, 2, 3 times the sine of theta over 2 is shifted down. So always be careful when you're dealing with quaternions. If you're taking code from other people, if you're trying to reproduce a paper, just make sure that you're using you're consistent, that you're not assuming that you have this kind of quaternion while some other person is using the one with the cosine as the first element. It doesn't change anything. The matrices will look a little different, but you can just shuffle elements around. It's just something to be aware of. And then let's see. If you invert the rotation, you basically in the quaternion you change the sign to the first three components, the vector one. And as I just said before, if you really need to visualize something, get the DCM and extract other angles. That's an easy way to do it. Okay, let's see. Error quaternion. So this is important, especially because at some point we'll code something that has a feedback control law based on Lyapunov theory, as you can see in the notes that I uploaded in the folder for yesterday. I use a Lyapunov-based controller, and I try to track a desired angular velocity and a desired orientation that changes over time. So in that particular simulation that we'll create, I am tracking a time-changing quaternion. What that means is that I need to be able to represent the error between where my spacecraft is, or how my spacecraft is oriented in space, and how I would like it to be oriented. So it's just the rotation between two frames, the real one, the one attached to your spacecraft, and the virtual one that you're trying to track. Exactly like you would chase a point in 3D, a trajectory that you want to overlap with. So the error quaternion, say that you have a reference frame that I call I, which is our reference frame, you, the observer, a commanded attitude reference frame that I call C, as commanded, and then the spacecraft, that is S. The error quaternion between S and C, which is probably the one that I will use in my control law, because it's the error, it's the difference between the desired orientation and the real one, is given in the following expression. So the quaternion that goes from S to C can be obtained as the product as between the quaternion that goes from spacecraft to I, which is basically the quaternion of your spacecraft, the one that you are integrating over time to represent its orientation with respect to your basis, the Earth, for example, and then the Q that represents now the inertial reference, our reference, with respect to the controlled one, which is basically the inverse of the QCI, and it's basically just a matter of changing signs. Let's see. For the once you have this, the error quaternion kinematics is the same one as before. It's just that now the elements in the Q matrix are the elements of the error quaternion, and this is valid for all angles as well. If you're representing a commanded reference frame that has a certain time evolution for error angles, and your spacecraft has to overlap with that, and you're able to calculate the relative order angles, the kinematics of those relative order angles are, the equations remain the same. It's just that now you have order angles, errors, and omega error. So it's a difference between angular velocities that goes in the place of where you had just omega before. Other things to be aware of. When you start getting serious about quaternions and you actually code something that uses quaternion, every time you run an operation on a quaternion, you must normalize it. Basically, you say you perform an operation, you are numerically integrating the quaternion, whatever comes out of it, take the vector and normalize it, so divide it by its norm, because software creates numerical errors, and even if they're tiny, they are accumulated over time, and at some point, you may have something that is not a quaternion anymore, doesn't have the norm of 1, and that has to be respected at all times. So you don't want to accumulate errors, because then your software eventually will collapse. Because everything is based on control laws, and everything that we do will be based on quaternions, and quaternions have certain properties. And if we start corrupting that piece of information in our software, then things will not work anymore. Let's see. If we have small angles, which is something that may be of interest, to wrap up these few slides, if you have sines that become approximated by the angles and cosines that become 1, well, then all the different 12 possible order angle sequences collapse into this expression here. You can prove that to yourself by looking at all the possible B and B inverse matrices that you have here. If you start assuming that, and you start, for example, setting to 0 everything that is sine of an angle times sine of another angle, because you will be multiplying the angles, for example, theta times psi. If you are linearizing, so you're looking at small rotations, then the product of two small angles becomes second order and negligible. So if you take these matrices, any of them, and instead of cosines, you plug in ones. Instead of the sines, you plug the angles and set to 0 any product of two angles. Then you will see that all of them collapse to this expression. And so this is the only one time when you can say that the omega vector is equal to just the time derivatives of the three Euler angles. Just straight, omega 1 is phi dot, omega 2 is theta dot, and omega 3 is psi dot. The angles have to be small. This is a linearized approximation for small angles. In general, this is absolutely not true. You cannot do this, okay? Just something to be aware of. But, you know, if you are small controlling, if say that your Euler angles are, again, error Euler angles, and they're representing a slight difference between a desired orientation and your actual orientation, and they remain bounded, then I would say that you can absolutely, you know, work with this as long as your linearization is, you know, good enough. And that's up to you to define. For quaternions, same kind of exercise. Every time you see a q multiplying another q, it goes to 0. And so you can easily demonstrate that your kinematics equations for q dot become simply 1/2. The q matrix becomes an identity matrix, and so you just get 1/2 times the omegas, and the last one is a 0. And since let's see. Let's see, how do we, well, q first of all becomes these. I'm thinking, how do we prove that? I will get back to you. I don't remember exactly how you get to this expression. It should be pretty straightforward. The cosine, first small angle, obviously the last element, it's a cosine, and it becomes a 1. If the angle is tiny, this is almost like saying that the three Euler angles are the same. Well, I'll get back to you on this, but these are basically the relevant simplified expressions if you have small angles and you're dealing with quaternions. Okay? We won't use them very much, to be honest. So actually, we may, you know, just dedicating half an hour or so to the first homework. I think this is a good spot to do it before I open a new set of slides that refresh astrodynamics and you know, cover other theory. This is really your final assignment for homework 1. It's important that you go through this exercise. It's basically now implementing everything that you've seen in that previous Simulink model that I will open again. So you start with the block that is implementing the Euler's equations of motion, and you know, that's what we saw before, either in scalar components or vector form. The one that I showed you is just the whole vector expression, solving for omega dot, and have the numerical integration. Okay. We use this matrix of inertia. This is one of our robots' matrix of inertia in the lab. We'll eventually change it, but this is just as a reference initial set of numbers. Then you add a block that implements the kinematics with the Euler angles 3, 2, 1 sequence. And we've done that. We've seen that. And now we add a block that implements the kinematics with quaternions. And we integrate those as well. Now I'm adding another operation. I want you to get from quaternions and convert them into Euler angles 3 to 1 and see if they match. Use the following initial conditions that are not here. Oh yeah, here. And run for 1000 seconds, which is what you've seen. I'm running the model for 1000 seconds. So the initial conditions are 5 RPM on all axes, as you've seen, for omega, and the identity DCM for the orientation. So identity matrix for DCM means that at initial time, at time 0, your rigid body and your reference frame are aligned with each other, obviously, which means that the Euler angles are all 3 zeros. And given the definition of quaternions, if you are aligned initially, look at this expression, theta is 0, so you have 3 zeros here and a 1 in the last element. And that's exactly what we had Not here. Let's see, what is the MATLAB function? Initialize here. So this is the J that I'm giving you in the in that slide that you need to use. This is the initial omega that I'm giving you in the slide that you need to use, and giving you a direction cosine matrix that is an identity matrix. These are the corresponding order angles and Q at initial time. Now, another good exercise you can perform, or identity matrix being DCM being identity matrix, another exercise you can have is the following. Go here, where I gave you the DCM. So if you have you have zeros off diagonal, and you have ones on the diagonal. Well, let's see what happens. Q4 becomes 1 plus 1 plus 1 plus 1. It's a 4, square root of 2, so Q1 becomes a 1. And then off diagonal terms are all zeros. So the vector component is the difference of those off diagonal terms, and it's just zeros. And this is one of those cases where Q4 is not 0, so you can just use this direct transformation rather than the alternatives. And so you easily see that if the DCM is the identity matrix, you get 0, 0, 0, and 1. For all angles, I'll leave it to you to show it, but basically, if you are performing no rotation, so at initial time the two reference systems are perfectly aligned, then your C1, 2, and 3 that we assembled before, they are basically matrices with a bunch of let's see, a bunch of ones. So you're multiplying identity matrices by 3 times, so you get an identity matrix. Okay. All right. So let's go back to what you should turn in, which is something like this. So we looked at this today. Now we are adding the kinematics equation with quaternions, which is nothing more than what you've seen in the slide. It's that 1 over 2, the capital Q matrix that looks like this, and it's including quaternions. There's a question? Yes.
Yes, sorry, Professor. I just wanted to ask if you can just zoom a little bit.
Let's see. I don't know how to do that. What's the combination? 1 second. And I lost the function, of course. What is this? Okay. Whoa. Oh. Okay. What was the combination? Control plus? Of course not. 1 second. Let me search. Yeah, it's not really. For some reason, I can't. I mean, I can, but it will take me a while. Let me see. I guess this is not any better, right? No. Let's see if we have a way here to make it bigger. Is it really impossible to see? Anyone?
I don't know, maybe it's just me, so don't worry.
No. How do I zoom in? How do I make the font bigger? That's the point, really. MATLAB font size. Okay, 1 second. I don't think I've ever done this. Does anyone know how to increase the font in MATLAB? I don't think I've ever done it. Well, sorry, doesn't seem like it's something I can do quickly.
Carlo,
Yes?
can you try to go in home, then preferences, and then you will be able to change the font.
You mean in MATLAB?
Yes.
Oh, thank you. Okay, right here. Oh, look at that. How about this? Did it do anything? Yay! Better?
Yes.
Yes, thank you.
Thank you. All right, so where was I? Yes, this is the kinematics equation. As you can see, it puts together that matrix. So that's what you will code. This shouldn't take too much time. Q dot is matrix times the omega vector and that additional 0. So that's what's happening in that block. And then I numerically integrated, as we've seen before. I need to feed back the quaternion because it's part of the Q matrix. I need to feed in the omega because it's needed. And Q0 is defined in the initialized file. And then I normalize. So this is an operation. It's taking a Q dot and creating a Q. I normalize. Okay? Always normalize. And this generates the Q given the initial condition. And then there is this additional block that does what I asked you, which is take the quaternion and try to look at the other angles that you extract from there. So let's see what's happening here. Well, I initialize the other angles to be 0. I don't know what they are. That will be my output. I put together the DCM as described in the slides as a function of the quaternions. So this is now a matrix of 9 values. And I start operating what I briefly mentioned before, that I look at the different elements and I know that this element up here, the C13, has to do with the second order angle, the theta. Notice though that I take that element and I massage it a little bit because I'm using an arcsine function, and an arcsine function can only digest something that is exactly between -1 and 1 in the argument. If it's 1.10 zeros and then a 1, MATLAB will give you a complex number, which is something you don't want. So in other words, this is another way to be careful about numerical errors that software may introduce. The same way you normalize a quaternion every time you need to, every time you perform an operation on a quaternion, the same way when you know that your output cannot be a complex value because it's an order angle here, then you be careful about what you feed into the arcsine function. So in other words, what I'm checking here is that if the absolute value of this element in the DCM is slightly outside 1, which in theory should not be, but it could be numerically a little bit outside of the range -1 and 1, then I just set it to be, if it's positive and a little above 1, I set it to be 1, and then same with for -1, and I compute the arcsine. And then I use the arctangent 2 function to compute the other angle. Let's see, this is psi and this is phi, using these other elements of the DCM, the element in the position 1, 2 and the position 1, 1. So we can go and look at, of course I closed it, 1 second, at those images I gave you. Let's see, the rotation matrices, attitude matrix, 3, 2, 1, right here. So let's see, I'm using, I already forgot. Okay, here, for, let's see, for psi, I'm using 1, 2, and 1, 1. Let's see if that makes sense. I'm gonna zoom in here. Okay, 1, 2 here, and 1, 1, this element. And so if you, if you use the 2 to solve for phi, actually, is it phi? Yeah. Then you get a tangent. You divide, cosine, cosine, you divide, and it goes away. You divide sine over cosine, you get the tangent. And so that's what I'm doing there. The arctangent of those elements give me the one of the other angles, the phi one. Okay, so here they are organized into phi, theta, and psi. Just a choice of organizing the vector. Is this making sense? And so now they should be the same order angle in principle, but I ran this, and well, when you run this for 1,000 seconds with the values I gave you, this is the behavior of the quaternions, the quaternion. It's a 4-component vector. You can also plot it in different 4 different plots. It's what it is. The norm is always 1. You can check that as well. Looking at a plot like this really doesn't tell you much. Let's see what we have. Now we have it's the same. Okay, these are now the ordered angles that I am obtaining from the quaternion. Okay, now these ones are, by the way I have computed them, obviously going to be between minus pi and pi. They can't go outside that because I've used arc sines and arc tangents, and so they're going to be wrapped around inside this range, and that's perfectly fine. While, as you recall, these were the other angles just coming straight off the numerical what is this? Oh, okay, no, this is comparison. So, okay, so this is comparing now the phi ordered angle with the, I forgot the legend, but it should be pretty obvious that the one that is continuously increasing is the one that is coming from numerical integration of the Euler's Euler angles kinematics, because there's no constraints, it can just grow. While the other one that is oscillating, it's the one coming from the quaternions. And well, there is overlap. They overlap until you reach pi. So, in MATLAB, I don't know if you know this, but you can select lines and actually remove them. At least, yeah. So if I do Control X, this will go away. And I see that the blue is just below it, and then I put it back on. So they are on top of each other until you reach pi, but then the fact that the other angles obtained from quaternions are obviously within the range pi, minus pi, pi, while the other one can do whatever it wants, makes them, it looks like they're diverging, but I don't know how to zoom out. Okay, here, how do you go? Here. But if you look more closely, when they start diverging, the behavior is the same. So if I were to shift down this portion here up to this vertical line, they will be on top of each other, and so on and so forth. So in other words, if you run a function, I think it's called a wrap 2 pi. There's a function in MATLAB that does that. If you were to apply the wrap 2 pi to this order angle phi that is growing, it will be constrained between minus pi, and they will be on top of each other. So I'm not showing it here, but you can easily show that to yourself. So this was the quaternion, I don't care. Let's see the other comparisons, if I can find them. What is this one? This is psi. Okay. Now this is same story. Again, my bad that I don't have a legend, but the blue one is the one obtained through the quaternion, then DCM, and then extracting the Euler angle. The red one is the one that can do whatever it wants, that is coming from straight integration. So again, they are on top of each other until this pi value, it could have been a minus pi, in this case they're just growing positive, and then the other one does whatever it can do by numerical integration, while the quaternion one is constrained, and so it has to jump from pi to minus pi. But again, if you were to shift the shape down, they would be just on top of each other, and that's a good sign. And so that if you look at the entire plot, you can see that the behavior is the same. They're just shifted by multiples of pi, nothing more. So this is also another nice exercise that you could do, is just make sure that you do the wrapping, the constraining between minus pi and pi of the Euler angles that are coming out of straight numerical integration. That's something you could do. And then let's look at the last one, if I can find it. I think is this one, maybe. Yes. Now this is theta. Theta, oops. Okay. This one instead is not ever going outside the range, apparently, also for the straight numerical integration. So if I actually go here, and if MATLAB allows me to select something, the line, I just want to erase the red one and show you that there's something else below it. There you go. So they are on top of each other. So here there's two things that I'm not doing too well in this example, and one is adding a legend. So in the here in the model properties, where I plot things, so I used to have legends for the first plots, but then for some reason I stopped. The comparison ones, yeah, see, they don't have legends. So you could definitely add that, and you can do that right away. So the first one will be A from Quaternion, and the other one is just EA. And so if I run everything again, at least one of those should be a little better. Okay, not this one, not this one. All right. Well, that underline, yeah, it made it a little messy. Anyways, I can fix that. But yeah, now I have a legend here. So what do you think about this assignment? This is very basic, in my opinion, unless you never used Simulink. I suggest that maybe you all have access to Simulink right now?
Yes.
Yes.
Why don't you guys start opening Simulink, and the first thing to do is, I don't know why this thing doesn't go away, is create a blank model and implement this function here. Let's start with that. So we have another 20 minutes. I think it's good to use some time to start playing with this and see where you get. This is your initialize. You only care about this line, the J, the omega 0 of the spacecraft, Euler angles, Q zeros. Okay, I'm gonna stop recording and I'll just be here for you where you work on this. Okay? Maybe I shouldn't stop recording actually, just in case you ask questions that are important and useful. All right. Anyone wants to share their screen while they do this? Anyone feels proficient with Simulink and wants to give it a shot? No judgment.
Okay. Maybe I can try.
Okay. I'll stop sharing my screen then. Go ahead.
Okay.
Very good. So while Miss Nocerino is doing this, everybody here is has used Simulink before, I'm assuming, right? Good.
Okay.
Let me see. Which one was it? Yeah. So in the coming days, while you work on these different blocks and you put them together, if you want to show me what you have, if you have questions, just send me an email, of course. Okay. Okay. I think it looks good. Now you go
There
up.
is an error, but
I'm sorry?
there is an error. Maybe there is a parenthesis that's missing. I'm checking.
No, but you want to have a parenthesis there.
Yes, maybe.
You probably have too many. No.
Okay. Now it's okay.
Yeah, you save it as, I don't know, homework 1, whatever. Yep.
Okay. Now we need the input.
By the way, you don't have to code things the way I'm showing you. I don't really care if you have initialized functions or you want to type things in the model properties. I mean, you do your own thing. These are just examples.
We can go to the other function. Okay. Now here.
Here you have, I can find it.
The error angles in.
Yes.
No. Okay.
Oh, I'm not sharing my screen, so you can't see it anymore.
Okay. Okay, I'll try. Omega and
Order angles.
Cambridge.
So some vector with the angles, for example.
Okay. So we can say that phi is 1. C is 2.
Okay.
Uh,
I think that's what I have, yes. Okay, so if you go in the files on Teams, under the folder level, well, not level, the lecture from yesterday, yeah, Monday. There's a folder called, really? Maybe it was today, sorry.
okay.
Yeah. Yes, EA Kinematics from Markley, just a few images. So probably not the first one. Yeah, I don't remember which one it is, second or third, probably yeah, it's the third, maybe. Right. So
Yes. Okay.
that one. You need to have, yeah, that one.
The 3 to 1 sequence. So
Yeah, the first table on top, yeah. So it's the last element to the right of that table, yes.
okay. So we can say that the elements of theta we can try to
I can tell you what it is. I mean, so, let's speed it up. So you have 0 in the first row. You have 0. Okay, you see it. Okay, sine of psi.
sine and cosine. Then second row 0 cosine theta cosine third element minus cosine theta times sine psi. Okay. Third row cosine theta theta times this could be the equation times omega.
Yeah. So you want to call maybe that EA dot just because they're not Euler angles, they're time derivatives, just to be.
Sorry,
No, the output, I think I would call them something else. Just EA is because they are the time derivatives. EA dot.
Yes.
I call them EA.
Dot.
Yeah.
Yes.
Okay.
Okay, really we don't need to.
What happened? I
Then
think
we can.
you erased one line.
Yes, the angle phi, which we don't need.
Oh, I see. Yeah. Okay. I mean, for now, without including also the quaternions, maybe you want to see if this runs by connecting those two blocks.
Yes. Okay. So we can add the integrator. And the initial condition we call omega 0. This has a feedback here. And then it here.
Yes.
This is so even if we don't have the file.
That is it's basically a diagonal matrix. The first element is 0.6. That's what I have.
Okay, 0, 0.
And 0.5, and then 0.2. And these are kilograms meters squared. Yes. Okay. Yeah.
Okay, and
No torque for now.
0, 0, 0.
Yep.
Okay, then we need
You need omega 0 and yeah, same down there. Just put a bunch of zeros.
Okay.
Of course, you can polish these and declare variables somewhere else, but I think this was 5 RPM, so it would be 555 that multiplies 2 pi over 60. Yes.
Let's just transpose.
Okay. This runs for 1,000 seconds, so you can put 1,000 there where you see 10. Oop. Oh, one thing that I didn't point out is the numerical solver. I think I left the default as you see there, but let me check. Model settings. Yeah, I have a variable step and left everything default.
Okay.
I think. Except I have ODE 45. Yeah, no, I have ODE 45, but maybe it works with the other one, yeah.
And variable step.
That's what I have. Yeah.
Okay. Okay. Just to show the output. Yeah, you have the integrator here.
Yes. And so actually now you have to feedback. Yeah, remove that constant.
Yes.
And feedback, yeah. Okay.
Let's try.
Yeah.
Yeah.
No errors the first time. Excellent. So you guys are very good with Simulink.
Yes, I've used it many times.
Good.
So
Okay.
we can see
Yeah,
the output.
you can plot omega, see if it looks like mine, just for fun. If I can ever find mine in this mess here. Let me run it again. Yeah.
Yeah, it seems like plot you showed before.
Yep. Okay. Well, thank you, Alessia. Much appreciated. So, yeah, you have done most of the homework really. Now you're missing the Q and the conversion from Q to other angles, but yes, that's what we're building for now. and then eventually we'll work on a much more complicated one with the momentum exchange devices, but I think this is a good starting point, and you can use some of these functions later on, okay?
Okay. I can stop sharing.
Yep. Any other questions? Anyone? We have 5 minutes. Please let me know if we're going too slow, too fast. You know, you may all be aerospace engineers, so you're very familiar with these things, or not. I was told that there was a mixed audience, so it's hard for me to understand exactly what is the right pace for everybody, but please let me know, okay? No questions, no comments? All right, I can certainly let you go a few minutes ahead of time. So before we do so, next time, which is tomorrow, let's see what I have. What I have is I would like for you to code eventually what I showed you today, which is the feedback loop on something that is actually in orbit. So I have a few slides refreshing astrodynamics. I think it's important for everybody to be on the same page. And then some slides on attitude, motion, stability. And even though the class is on momentum exchange devices, I can certainly cover spin stability, gravity gradient, and all those other means that we initially discussed, if that's of interest for you guys. And then we can eventually move to the equations for the variable speed control moment gyros. What do we think? Sounds like a plan?
Yes, it's okay.
Do tell me if you know all this stuff. Okay. Means yes, means no. Means it's okay to do it again. Okay. Well, thank you, everybody. You have a good rest of your evening, and I will see you tomorrow.
Okay.
Thank you.
Thank you so much.
Bye.
Bye.
Thank
Bye-bye.
you.
Bye.